Hello students, welcome back to the next module of the chapter Oscillation. Students, in this module we'll cover a very important concept of time period of spring block system for vertical vibrations. So let's start the concept. Spring block oscillator system. Now students, as you can see in the diagram, we have considered a spring having a natural length L. The upper end of the spring is attached to a rigid support, and to the lower end we have attached a block of mass M. Let K be the spring constant of the spring. Students, since the block has a mass M, therefore gravitational force acts on it in the downward direction. As we know, this gravitational force is nothing but its weight mg acts in the vertically downward direction. Now what happens? Because of this gravitational force, the spring starts extending. So there is an extension produced in the spring. As the spring extends, students, within the spring force will be produced, which will be acting on the block in the upward direction. This will continue till the two forces balance each other and it acquires a equilibrium position as shown in this diagram now. Let x0 be the initial extension required for acquiring the equilibrium position. Now what exactly happens at equilibrium position? You can clearly see we have two forces as discussed by me. Weight mg acting downward direction and spring force F is equal to, general formula is F is kx. Since for equilibrium extension is x0, therefore I will write it as kx0 in the upward direction. At equilibrium position, this block is at equilibrium. That means net force along y is equal to 0. That means total downward force mg is exactly equal to the upward force kx0. Now students, this equilibrium condition in the case of vertical vibrations can be used for MCQ solving. So I can write very important condition for equilibrium. mg should be equal to kx0, where x0 is the initial extension. This can be very useful for finding either spring constant, that is k is mg by x0. I can therefore find k provided m and initial extension x0 is given, or I can find x0, that is x0 is equal to mg upon k. I can find x0 if m and k are given. So remember students, for vibrations, vertical vibrations of a spring, this becomes a very handy formula, equilibrium formula. Mg is equal to kx0. We can find either k or x0. Now at equilibrium position it will not vibrate on its own, therefore we have to disturb the equilibrium position. Let the spring be further displaced from its equilibrium position by x, and now as soon as you release it, the vertical vibration starts. Now you can very clearly see x is the maximum displacement from mean position, which is nothing but amplitude. Now since the spring mass system vibrates, now this is, remember, a vertical vibration. Now it will definitely have some angular frequency. Without going into derivation, we can straight away write angular frequency is root of k by m, which we have already studied in our earlier modules. Students, time period of vibration, therefore t is equal to 2 by omega. If I substitute it here, this becomes t is equal to 2 pi, and that becomes root of m upon k. Students, this also we have seen it in the earlier modules. As frequency is reciprocal of time period, therefore f is equal to 1 upon 2 pi root of k by m. Students, in these formulas, the first formula is valid for vertical vibrations. Second, third and fourth are valid for both horizontal as well as vertical vibrations. Very important. Now let's solve a multiple choice question on this. As you can see, a body of mass 980 gram is made to oscillate on a spring of force constant 4.9 Newton per meter. Then the angular frequency of the body is, and four options are given to us. Straight away I can use the formula. I have to find omega. We know omega is root of k by m. K is directly given to us as 4.9 Newton per meter. That is, it is expressed in SI unit. but mass is given in gram. So let's convert it to kg, that is 980 into 10 raised to minus 3. Let's take that 10 raised to minus 3 in the numerator. Therefore, I can write the next step as 4.9 into 10 raised to 3 upon 980. The numerator can be rearranged as 490 into 10 upon 980. Advantage I get is I can straight away cancel 490 into 2 is 980, and therefore the next step omega is equal to root of 10 upon 2, which is nothing but root 5, and therefore the answer for this question is root 5 radians per second. That is nothing but our option yes, C. So students, we learned a very important concept of vertical vibrations of spring. That's all in this module, students. See you in the next module.